What is up, amigos? Today we have the aerodynamics of a jerry can. And growing up, these were the type of cans for gasoline that I saw all the time. So even to today, if I see one of these cans, I pretty much immediately know that there's going to be gas in there. Although maybe there won't be gas in there, I need to usually take off the top and check inside to see if there is. But I have a good idea as to there's probably going to be gas in there. It's the type of can that would have gas. And they usually come in green. I've seen them sometimes in brown, a few ones, but I've never seen them in blue. So we have the aerodynamics here with different cut planes downstream. And I've put the jerry can at an angle, it's like you were pouring some gas out, for example. And this has made the wake really interesting. So you have pretty much two lobes forming, one at the top, one at the bottom. In the middle of the wake, there's like this truncation of the wake. So why does that happen? The reason why is because from the two top corner, like the top corner and the bottom corner, because the flow hits the jerry can at the front, then it separates on the edges. It doesn't have any time to reattach because as soon as it tries to reattach, it's already past the jerry can and now we have a big wake. Around the middle of the jerry can, so let's say we have the nozzle and we go in the free stream direction, so horizontally, the flow will separate around the edges, but then it will start to reattach on the jerry can before it hits the back. So then this allows the can here to be a little bit more streamlined. So that's why we get this cool truncation shape happening. And the truncation is quite varied, like it does move around a lot, which indicates that this jerry can is very bluff. These are the exact same planes, but now with a sub drag. And we can see just how draggy this jerry can is. We have a lot of drag very close to the jerry can, but it dies out fairly quickly as we go downstream. That indicates that this is a fairly bluff body, but I think because of that middle section, the wake does die out much quicker than what it might if we had the jerry can upright. I can tell you that the drag coefficient of this is 0.52. So it's not too bad. I think it's better because we have it at an angle. If it was upright, it would probably be a bit higher, I think. We have a Y plane now, which is just on the edge of the jerry can. So it's not hitting the jerry can, it's just like stationed off a little bit. And this shows exactly what I was saying before. So on the top corner and the bottom corner, you do have this wake forming, and that's because the flow does not have time to reattach before it hits the end of the jerry can. In the middle part, it does have time. That's why we get a smaller wake happening here. That's really cool. And this is the exact same plane now with a sub drag. And this confirms what we think, which is the top and bottom are where most of the drag is coming from. We can see these drag production areas here. The bottom part is a little bit more draggy than the top part, and that's because it's not nearly as varied. So the top part, if you remember the geometry, as we'll see a bit later again, it had the nozzle, then the handles, and then the edge, like the top edge. So that was a little bit more varied, which indicated that like there's some more turbulence there, which helps keep the flow a bit more attached, and also it's not as bluff, it's not as blunt, so we don't get as much drag from the top as the bottom. So now we have a Y plane going through the middle of the jerry can. And the two things that stand out to me, first of all, is that the wake is really big as you'd expect. It really just flares out. That's because there's redirection of the flow in these areas, and it has to like hit the free stream and then it straightens up more. The second thing that strikes me is that there is not a lot of flow recirculation behind the jerry can. Most of the flow is fairly still like linear, like it goes downstream fairly quickly. There's not a lot of recirculation. I think that's because the jerry can is fairly thin. So because it's fairly thin, you have the flow around from the free stream areas, and that's kind of entraining the flow a little bit more downstream and helping it stay more streamlined as opposed to just recirculating around if you had like a sphere, for example. And even though we didn't have as much recirculation as we might have with other bluff bodies, the drag production is still very high. As I mentioned, the drag is 0.52, the drag coefficient. Also, the lift coefficient was not that much. It was 0.05, which indicates there is a little bit of lift being produced, but not too much. That's probably because of the asymmetry in the jerry can's geometry, and it's like turned down a little bit. If I were to turn this 90 degrees more, I imagine that might be producing a little bit of downforce. Instead, you get the opposite thing happening. This is a Z-plane below the jerry can, so it's not even hitting the jerry can yet. And it's pretty cool. We can still see the wake because the wake is so big, it flares out so much. But interestingly, there is a two-dimensional periodicity to it. So left and right, you can see as time progresses, it sheds one side, then the other side, and etc. Now, that's interesting because I would expect a bit more of a three-dimensional effect from the jerry can because we're like right on the edge, even further from the edge than that. So I would have thought there'd be some sort of three-dimensionality there. But it seems like the two-dimensional periodic shedding is dominating the flow. So this Z plane is a little bit higher now. It's now hitting the jerry can. It's about 1/4 up. And we can see that this area is really where most of the damage is occurring, I think. We have a big wake. It's three-dimensional because the two-dimensional fluctuation is not nearly as crisp as what it should be. That indicates that there is three-dimensionality coming off from that corner, which is interesting because the plane that we saw just before, which is lower, didn't have that three-dimensionalness to it. It had only the two-dimensional side to it. So we had to go closer to the jerry can for that three-dimensional aspect to take into play. The sub-drag shows that there's just a lot of drag coming off of this plane at the moment. Even if you go upstream, like just at the edges of the front of the jerry can, look at how much it just flares out and you're getting drag being produced already from there, which is not a good idea. You want to really delay drag being produced as much as possible to reduce the drag, but obviously it doesn't happen here because the jerry cans are not that aerodynamic, generally speaking. So this plane is now going through the handles and just above the nozzle. And we can see the handles, I think, do make a big difference because the wake is a little bit smaller and it's more two-dimensional than the other plane that we saw further down on the jerry can. So I think that the handles are helping stabilize the flow a little bit more. And why would that be? Partly because the flow can sort of be redirected a little bit better. It doesn't have to get redirected at one sudden. It can take a bit more time to do that. Secondly, there's some sort of vorticity coming off of these handles which help re-energize the flow a little bit, perhaps, and help it stay attached a little bit more, or at least not separate nearly as violently. So even though we had a little bit smaller wake, we still have quite a bit of drag coming off here, and a way to reduce this drag is to potentially streamline the corners a little bit more. So chamfer them and potentially round them a little bit more, and we could reduce the drag there. So that's in this video. Make sure to like, subscribe, and if you want to get better at CFD and or theory yourself, check out courses at link description, and I'll see you next time. Peace, amigos.